All right, let's dive in. Today, we're tackling parallel processing. And to kick things off, we're going to be looking at something called threads. You sent us this excerpt from a programming series. And to be honest, it looked kind of intimidating at first glance.
Yeah.
But I have a feeling it's going to be one of those aha moments once we really break it down.
I think you're absolutely right. They're really a fundamental concept in programming, and understanding them can completely change the way that you think about software.
Well, I'm ready for that aha moment. The source starts with this analogy of a timeshare villa to explain time sharing. I thought that was pretty clever. You know how multiple families can enjoy the same villa, but just at different times?
Yeah. The timeshare analogy is a good starting point. Back in the day with single-core processors, it was really all about creating this illusion of multitasking. The processor would rapidly switch between different programs, giving each one a tiny slice of processing time, just like those families taking turns at the villa.
Okay, so it's like each program is getting a little bit of time to use the facilities,
right?
But then has to get out of the pool so the next family can come in.
Exactly.
Okay, that makes sense.
But it really highlights the limitations of that approach. Each program was essentially being shamed into taking a really short turn before being pushed aside for the next one.
So it wasn't true multitasking. It was just really, really fast task switching.
Yeah, exactly. And as programs became more complex and more demanding, that approach just couldn't keep up. It's like trying to fit a whole family reunion into that timeshare villa all at once. Chaos.
Right. Not ideal. The source mentioned something about multi-core processors coming to the rescue.
Yeah, that's where the real breakthrough happened. Multi-core processors essentially gave us multiple villas, multiple processing units that can actually handle tasks concurrently. But to take full advantage of that, we needed a way to split programs into smaller, independent units of execution. And that's where threads come in.
Okay, so threads are like dividing that big family reunion into smaller groups, each with their own designated villa to hang out in. Much more peaceful.
Precisely. Threads allow a program to divide itself up into these smaller units of execution, each of them capable of running simultaneously on a different core, instead of like one chef trying to cook a multi-course meal single-handedly. Imagine having multiple chefs working in parallel, each focusing on a specific dish.
No, that's what I call efficient cooking. So instead of waiting for one function to finish before moving on to the next, threads let programs tackle multiple tasks concurrently. Does that mean we can finally say goodbye to those dreaded application not responding messages?
That's one of the big benefits, yeah. Think about something like, that you use every day, like your web browser. With threads, it can be downloading files in the background, rendering web pages, and responding to your clicks, all seemingly at the same time.
No more staring at a frozen screen while waiting for a page to load. I like the sound of that. But the source also throws in a bunch of thread-related terms like thread function, thread count, thread ID. Can we unpack those a bit?
Absolutely. Let's think about it like managing a team of workers. You need to give them instructions, assign tasks, track their progress. That's essentially what all these terms allow us to do.
Okay, so maybe we can group them by their function. First, we need to create these threads and give them something to do.
Right. Thread function is basically the set of instructions that tells a thread what to do, its job description. And thread create is like hiring that worker and getting them started on their task.
And we need a way to manage them and make sure everything's running smoothly.
Exactly. Thread count tells us how many active threads we have, which is important because too many threads can actually hurt performance if our system can't handle them all efficiently.
Too many cooks in the kitchen, so to speak. And what about thread ID? Is that like giving each worker a unique badge number?
You got it. Thread ID is a unique identifier for each thread. It's essential for keeping track of them individually. Just like each worker needs a unique ID card to access different areas of the factory.
Okay, that makes sense. We need to keep track of who's doing what. But how do we know if they're actually doing their jobs? Is that where thread status comes in?
Thread status tells us whether a thread is running, waiting, or finished, like a progress report for each worker.
So we're creating threads, assigning them tasks, giving them IDs, monitoring their progress. Sounds like a well-managed factory so far. But what happens when a thread is finished with its job?
Well, we need to let them go home for the day, right? That's where thread close comes in. It cleans up after a thread has finished its work, freeing up system resources for other tasks.
Got it. So we hire our workers, give them instructions, track their progress, and then let them go when they're done. But I'm noticing some other terms here, like thread set priority and thread get priority. What's the deal with those?
Thread priority. Now that's where things get really interesting. This is like deciding which tasks are more urgent. and need to be completed first.
So if a thread has a higher priority, does that mean it gets to cut in line and hog all the resources?
It's not quite that cutthroat, but it does give higher priority threads a slight advantage when competing for CPU time. It's like having a VIP pass at a concert. You might get to skip the general admission line, but you're not the only one with that privilege.
So we're not talking about creating a thread hierarchy,
Yeah.
where some threads are inherently more important than others.
No, it's more about strategically allocating resources based on the task at hand. For example, if you have a thread that's responsible for updating the user interface, you might want to give it a higher priority, so the application feels responsive and snappy, even if other background tasks are running.
That makes sense. We don't want the user to feel like they're stuck in a time-shaming situation while the program is busy doing other things in the background.
Exactly. It's all about optimizing that user experience.
Yeah.
And thread set priority and thread get priority are simply the commands that we use to assign and check these priority levels.
Okay, this is starting to make a lot more sense. We create threads, assign tasks, give them IDs, monitor their progress, and we can even prioritize certain threads for optimal performance. It's like we're conducting an intricate symphony of parallel processing. But choosing those priority levels seems like it could get tricky.
You're right. It's not as simple as just bumping everything up to the highest priority. There are some important trade-offs to consider.
Like what? What happens if we go overboard with the VIP passes?
Well, too many high priority threads can actually lead to a situation called contention, where they're all fighting for resources and slowing each other down. It's like having a rush hour traffic jam, even though everyone has a fast car.
So there's a delicate balance to strike. Too few threads, and we're back to the time-shaming problem. Too many high-priority threads, and we create a new kind of bottleneck.
Exactly. Finding that sweet spot where we're maximizing parallel processing without overloading the system is key. And that's where a deep understanding of threads and how they interact with each other and the system as a whole becomes crucial.
That's like, we're not just writing code. We're orchestrating an intricate performance, where each thread plays a crucial role in creating this harmonious and efficient whole.
That's a great way to put it. And as we delve deeper into this world of parallel processing, we'll uncover even more fascinating aspects of how threads are shaping the way we interact with technology.
I am excited to keep going. Okay, I'm starting to see the bigger picture here. Threads are like this hidden workforce powering our digital lives, making everything smoother and faster. But I'm curious, are traditional threads the be-all and end-all of parallel processing, or are there even more advanced techniques out there? I mean, technology is always evolving, right?
You're absolutely right to question that. While threads have been incredibly valuable, they do have their limitations, especially as we move towards even more demanding computing tasks.
What kind of limitations are we talking about? Do threads get stuck in their own little traffic jams?
In a way, yes. Remember how we talked about contention? When too many high-priority threads are competing for resources? As we pack more and more cores onto processors, that problem can become even more pronounced. It's like having a city with a fantastic network of roads. But if everybody decides to drive at the same time, you're still going to have gridlock.
So even with all those cores, we can still hit a bottleneck.
Exactly. And there's also the overhead of managing all those threads. It's like having a huge team of workers, but spending all your time just coordinating their schedules instead of actually getting work done.
Okay, so what are some of the alternatives being explored? What's the next frontier in this parallel processing saga?
Well, there are some fascinating new approaches emerging. One is called data parallelism, where instead of dividing the program itself into threads, you divide up the data that it's working on. Imagine you have a massive data set of images you need to analyze. Instead of having one thread analyze each image one by one, you could split those images into smaller batches and have multiple threads process those batches simultaneously.
So it's like having multiple assembly lines working in parallel, each one dedicated to a specific part of the process.
Exactly. And another approach is task parallelism, where you break down a complex problem into independent tasks that can be executed in any order. Think of it like building a house. You can have different teams working on the plumbing, electrical, and framing all at the same time without having to wait for each other to finish.
Okay, so we're moving from a synchronized dance to a more free-flowing jam session, where each thread can groove to its own rhythm. But how do these new models address the communication bottlenecks that traditional threads can face?
That's a crucial point. One way is by using specialized hardware, like GPUs or graphics processing units. They're designed for massively parallel computations. with thousands of tiny cores that can work together incredibly efficiently.
So it's like having a superhighway, specifically for data traffic. No more bottlenecks or rush hour delays.
Exactly. And there's also been a lot of progress in developing new programming languages and frameworks that are designed to express parallelism more naturally and intuitively.
So we're giving programmers better tools to orchestrate this complex dance of parallel processing.
Exactly. These new languages can abstract away some of the low-level complexities of managing threads, allowing programmers to focus on the logic of their algorithms, rather than getting bogged down in the details of synchronization and communication.
That sounds like a huge win for developers. It's like having a conductor who can speak fluent parallelism and guide all those threads to create a beautiful symphony of computation.
A perfect analogy. And these advancements are opening up incredible possibilities in fields like artificial intelligence, scientific computing, and even everyday applications like web browsing and video streaming.
It's amazing to think that something as seemingly technical as threading can have such a profound impact on how we experience the world around us.
It really highlights the importance of understanding these fundamental concepts, even if you're not a programmer yourself. Knowing how computers work at their core gives you a deeper appreciation for the technology we use every day, and empowers you to make more informed decisions about the tools you choose and how you use them.
It's like having a peek behind the curtain and seeing all the gears turning, all the threads weaving together to create this digital tapestry that we interact with every day. And it makes me wonder what other exciting advancements are just around the corner.
Well, the pursuit of ever faster and more efficient computing is driving innovation across countless industries, from healthcare and finance to transportation and entertainment.
It's an exciting time to be alive, that's for sure. But with all this talk about parallel processing and the future of computing, it's easy to get lost in the technical details. I'm curious, what's the key takeaway you want our listener to walk away with today?
I think what struck me most throughout this whole deep dive is that threads, they're not just some abstract programming concept. They're actually the invisible force behind so many of the digital experiences that we just take for granted.
You're absolutely right. They really are woven into the fabric of modern computing, enabling everything from those responsive user interfaces we were talking about to those really complex scientific simulations. Yeah, we started by looking at the limitations of single-core processors and how they had to resort to time shaming to juggle all those programs. Then we saw how multi-core processors and threads came along and completely revolutionized the game, allowed for true parallel processing. It's fascinating how something so fundamental can have such a massive impact.
It really is. It highlights how interconnected hardware and software really are. We need those powerful processors, but we also need those clever ways to harness that power through concepts like threads.
Yeah, and it's not just about throwing more cores and threads at a problem, right? We learned about the importance of thread management, how assigning priorities and understanding concepts like contention can really make or break a program's performance.
Exactly. It's like conducting an orchestra. You need to understand the capabilities of each instrument and how they all work together to create a really harmonious sound. And similarly with threads, it's all about orchestrating their behavior to maximize efficiency and create that smooth user experience.
And we even got a glimpse into the future of parallel processing, exploring how new approaches like data parallelism and task parallelism are pushing the boundaries of what's possible. It's like we're moving from a world of rigid time slots to a much more fluid and dynamic way of processing information.
Absolutely. And that evolution is being driven by that ever-increasing demand for computational power in areas like AI, big data analysis, and scientific research. As we're tackling more and more complex problems, our ability to process information in parallel becomes even more crucial.
So as we wrap up this deep dive into the world of threads, what's the one key takeaway you'd like our listener to remember?
I think the most important thing to remember is that threads, they're more than just a technical detail. They're a fundamental concept that underpins much of modern computing and shapes our daily interactions with technology, even if you're not a programmer. Understanding how threads work, even at a high level, gives you a deeper appreciation for the ingenuity behind the systems that we rely on every single day.
It's like having a secret decoder ring for the digital world.
Exactly. And as we move toward even more powerful and interconnected computing systems, the ability to think in parallel will become increasingly valuable, not just for programmers, but for anyone who wants to understand and leverage the potential of technology.
So here's a final thought to ponder as you continue your exploration of this fascinating world. As parallel processing continues to evolve, what role will you play in shaping its future? Will you be a passive consumer of technology, Or will you seek to understand its inner workings and use that knowledge to create, innovate, and solve the challenges of tomorrow?
The choice is yours. And that concludes our deep dive into the world of threads. Until next time, keep exploring, keep learning, and never stop questioning how things work.